Okay, so we need to find the interval of convergence of this power series, which means to determine the interval values of x for which this will converge. This infinite series will converge. And so the tests that they recommend are either the ratio test or the root test for power series convergence testing. So, or for finding the interval of power series, because power series have powers, exponents, and when you do the root test, you can undo some of those exponents. You can get rid of some of those exponents, but sometimes that's actually more complicated for some of the factors, such as factorials. We don't want to introduce that mess, so we'll actually do the ratio test, and I actually find that using the ratio test works for most of the problems that I encounter. So the ratio test says when the limit of the ratio as k goes to infinity of the absolute value of the ratio of the k plus 1, the ak plus 1 over ak is less than 1, when that's true, then you have convergence and ak converges. So we just need to find ak plus 1 and divide it by ak, simplify as much as possible, and figure out what x values will cause this to be true. So let's just be very careful when we plug in k plus 1 here. Let's use parentheses to actually be very careful with that for parenthesis k plus 1. Or you might forget that this is actually, don't just stick a plus 1 up here. 5, okay, not 5k plus 1, 5 parentheses k plus 1, parentheses, okay, k plus 1. Now, a fraction divided by a fraction, we keep change flip, so it's ak plus 1 times the reciprocal of ak instead of dividing by ak. And so now we have some things dividing into 1, turning into 1, 6 divided by 6, for instance. That's about it. So we need to break up using properties of exponents. Remember, a to the, let's do x to the a times x to the b equals a to the x to the a plus b, or you could split that back up the other way. And so, and also, I want to say, yeah, xy to the a also equals x to the a, y to the a. That's a property of exponents. We'll use a couple of those. So let's simplify this. Also, properties of factorials. This is one index higher than this, k plus 1. One number higher, so we'll just step that down by 1. So it's k plus 1 times k factorial. Now the property of exponents that we want to use, 4k plus 4. Actually, we could have split that up. Do that in the next step. Times 5 to the k, k to the k. And then we have 5k plus 5 to the k plus 1, k factorial, okay. Let's cancel while we can. That's about it so far. K plus 1. This, using the first property I wrote down for exponents, split this up. We can actually, well, no. Let's keep it like that. K to the 4th. 5 times over. Okay, we can actually do some work on this. Make this, well, let's split this up first. 5k plus 5 to the k times 5 to the k plus 5 to the 1. Now that's the same property, splitting this up, of x to the 4k. Remember, we're doing a limit, so we don't want to forget about that. But we won't apply the limit yet. We have all kinds of cancellation that can happen. This is actually 5 times k plus 1, which k plus 1's cancel. This is actually 5 to the k, k plus 1 to the k. Pull out a 5, and that becomes 5 to the k, and then you have left over k plus 1 to the k. 5 to the k's cancel. Let's clean up what we have here. X to the 4th, k to the k over k plus 1 to the k times 5. Limit. That's it. So 1 over 5 can come out to the front of the limit. Actually, x can come out. X doesn't have anything to do with k. And this is a limit of k. Let's pull that out as well. And now what I have left is a fraction being raised to the kth power. And we've done limits by this point. Hopefully you've done limits like this before. This is infinity over infinity. This will approach infinity over infinity raised to the power of infinity. And what we would like to see is a nice indeterminate form that we can apply. We're justified in applying L'Hopital's rule. And that would be infinity over infinity or 0 over 0. Not what we have. We have infinity over infinity to the power of infinity. That's not quite right. We need to do some modification. Since we have a k in the exponent, a variable approaching infinity in the exponent, we need to apply the logarithmic trick. The little rule that we have is if we have something, we can actually say, well, might be handy to do e to the natural log of that something, right? That these, e to the natural log of x equals x. That's a property of exponents and logs, exponentials and logs, and so that's a logarithmic property. So we're going to employ that trick here.